Take every planet in the solar system: Mercury, Venus, Mars, Jupiter, Saturn, Uranus, Neptune. Line them up edge to edge and try to squeeze them into the gap between Earth and the Moon. They fit, just barely, but they fit. All 7 of them. The entire planetary roster of our solar system tucked into a single orbit. And most people look at the Moon and think it's impossibly far away. That is the central trick the sky plays on us. The Moon hangs up there looking distant, mysterious, unreachable. And yes, it is 250,000 miles out. That sounds enormous. But in the context of space, in the context of what a solar system actually looks like, the Moon is practically touching us. It's right here. And the fact that it's right here, that specific narrow distance, is one of the most consequential facts in the entire history of life on this planet. The Moon did not just happen to end up where it is. Its position is the result of a catastrophic collision, billions of years of physics, and a slow drift that is still happening right now. And the distance it sits at has shaped Earth's climate, sculpted its coastlines, stabilized its axis, and made complex life possible in the first place. So let's actually talk about the Moon, not as a pretty light in the night sky, as the thing that built the world you live in. The average distance from the center of Earth to the center of the Moon is 238,855 miles. That sounds definitive, but the Moon does not travel in a perfect circle. Its orbit is an ellipse, which means the distance shifts constantly. At its closest point, called perigee, the Moon closes in to about 225,623 miles. At its farthest, apogee, it pulls back to roughly 252,088 miles. That's a swing of about 26,000 miles every single month, back and forth, closer and farther. That swing is not just a technicality. When the Moon is near perigee and happens to be full at the same time, you get what people call a supermoon. The Moon can look up to 14% bigger and 30% brighter than when it's at apogee. More importantly for Earth, the gravitational pull is noticeably stronger at perigee. Tides run higher and lower. Coastal flooding risks increase. Fishermen have tracked perigee tides for centuries without knowing the word for them. And here's the thing about those tides. They're not a quirk. They are one of the primary engines that drove life on this planet forward. We'll get there. But first, how does 238,855 miles actually fit all those planets? The combined diameters of Mercury, Venus, Mars, Jupiter, Saturn, Uranus, and Neptune adds up to about 247,000 miles. The average Earth-Moon distance is 238,855 miles. The math is tight. At average distance, it's a squeeze. And at perigee, the planets don't fit. But at apogee, when the Moon pulls out to 252,000 miles, you have room to spare. Room for every planet in the solar system plus Pluto, which has been demoted but deserves to be included anyway. The reason this fact hits so hard is that it destroys your intuitive sense of scale. Our solar system feels enormous. Jupiter alone is 88,846 miles across. Saturn is 74,897 miles wide. These are worlds so large they could swallow Earth a dozen times over. And yet, the gap between you and the Moon could eat all of them in a row. This is what happens when your brain builds a mental model of space from pictures that are not to scale. Now here's something those pictures definitely never show you. The Moon is moving away from us. Right now, as you're watching this, the Moon is drifting outward at about 1.5 inches per year. That was not a guess or a model. It was measured. In 1969, the Apollo 11 crew placed a small panel covered in retroreflectors on the lunar surface. A retroreflector bounces light straight back to its source regardless of angle. Since then, observatories in New Mexico, France, Italy, and Germany have been firing laser pulses at that panel, measuring the exact time it takes for the light to bounce back. The round trip takes about 2.5 seconds. And year after year, that round trip takes just a tiny bit longer. The moon is getting farther away at a rate we can now measure to within a fraction of an inch. Why? The same force that creates our tides. Earth's rotation drags the water in its oceans forward, creating a bulge of water that pulls slightly ahead of the moon as it orbits. That tidal bulge exerts a small gravitational pull on the moon, like someone throwing a rope forward and tugging. The moon gains a tiny bit of orbital energy from that pull, which causes it to spiral outward, slowly, imperceptibly in a human lifetime, but inexorably. 1.5 inches per year does not sound threatening. But let's run it backward. The moon has been pulling away for about 4.5 billion years. At that rate, with known physics, it was once about 14,000 miles from Earth's surface, 17 times closer than it is today. The moon rising over the horizon in those early days would have looked 15 to 20 times larger in the sky. And the tides it generated were not the gentle 6-foot swings we see on most coastlines today. They were cataclysmic, walls of water hundreds of feet tall rolling across the young planet's surface. About 2.46 billion years ago, the moon was around 200,000 miles away, measurably closer, and its tidal effects were still dramatically more powerful than today. The Earth itself spun faster then. A day on early Earth lasted only 5 or 6 hours. The moon's gravitational drag has been slowing that rotation down ever since. Which raises the obvious question: where did the moon come from in the first place? About 4.5 billion years ago, the solar system was still a chaotic, crowded place. The planets were young, still sweeping their orbits clear of debris. Earth was essentially fully formed, but it shared orbital space with another object, something roughly the size of Mars, which scientists have named Theia. The two were on a collision course. The impact was not a glancing blow. It was an oblique, full-scale planetary strike. Theia hit at around 45 degrees and at a speed that computer simulations estimate exceeded 20,000 miles per hour. The collision was so violent that both Theia and a significant portion of Earth vaporized and melted. An enormous cloud of rock vapor and molten debris was blasted into orbit around what remained of Earth. Within hours, possibly days, that debris began to coalesce under gravity. The moon was born inside a ring of planetary wreckage. The evidence for this is locked inside the lunar samples Apollo astronauts hauled back. Nearly 900 pounds of rock and dust collected across 6 missions. When scientists analyzed those rocks, they found something strange. The isotopic signatures, the specific ratios of oxygen, titanium, and other elements, matched Earth's rocks almost perfectly, far more closely than rocks from Mars or asteroids. If the moon had formed somewhere else and been captured, the chemistry would be distinctly alien. But it's not. The moon is essentially made of Earth. There's also a subtle but important isotopic difference. Lunar rocks show a slightly higher concentration of a specific oxygen isotope that traces back to Theia's contribution. The lunar zinc signature confirms the violent high-temperature origin. Moon rocks are depleted in zinc compared to Earth rocks, consistent with zinc boiling away in the heat of the impact. Everything points to the same story. A Mars-sized object hit the early Earth. That collision blasted material into orbit. That material became our moon. It is the most violent thing that ever happened to this planet. And we survived it. The far side is not the dark side. It gets just as much sunlight as the near side. It just never faces Earth. It's covered in more craters, fewer of the dark volcanic plains we see from our backyard. It looks like a completely different world. And it's been sitting right there, completely unknown, for the entirety of human civilization. Of all the strange things proximity has done to the moon, tidal locking might be the most philosophically unsettling. An entire hemisphere of the nearest world to Earth, invisible to every human who ever lived. But here's the part that actually changes everything about how you see the planet you're standing on. The moon's gravitational pull does not just move water. It moves Earth itself. It holds our planet's axis at a steady angle of 23.5 degrees. That tilt is why we have seasons. Why summer days are long and winter days are short. Why temperatures swing predictably between extremes. Why agriculture is possible at all across broad swaths of the planet. Without the moon, that tilt would not stay at 23.5 degrees. It would wander. The gravitational influences of Jupiter, Saturn, and the other planets would pull Earth's axis in competing directions, with nothing large enough nearby to stabilize it. Scientists calculate that without the moon, Earth's axial tilt could swing anywhere from nearly upright, 0 degrees, to nearly sideways at 85 degrees. And it would do that repeatedly over millions of years, in patterns that are essentially chaotic. Look at Mars for comparison. Mars has no large moon. Its axial tilt has swung dramatically over geological time, possibly by as much as 90 degrees, based on evidence in its ancient geology. What were once polar ice deposits are scattered at mid-latitudes. The climate has been so erratic over Mars's history that liquid water could not have persisted long enough for complex life to get a foothold, even if temperatures were sometimes right. Mars is, among other things, a planet that lost the axial stability lottery. Earth got lucky because something the size of Mars smashed into it. Now here's what the moon's proximity has done to life specifically. Tides. Early Earth's tides were enormous. The moon was much closer, pulling harder, and the planet spun faster, which amplified tidal forces even further. The coastal zones of early Earth were extreme environments. Vast tide pools that flooded and emptied on rapid cycles, concentrating minerals, organic molecules, and eventually the chemistry that preceded life. Some origin of life researchers believe tide pools weren't just incidental to life's emergence. They were the engine. More recently, though still 400 million years ago, researchers studying fossil fish have found evidence that the ancestors of all land vertebrates, including every human being who ever lived, first developed lungs and weight-bearing fins in regions with extreme tidal ranges. The theory is straightforward. Powerful tides regularly stranded fish in shallow pools and exposed them to air. The individuals with the ability to breathe in those conditions survived. Those that couldn't, didn't. Over generations, that pressure built the body plan of the first land animals. The moon pulled the ocean back. The fish that survived what got left behind eventually became you. Take the moon away, and that slow, cumulative process might never have had the stability to run. It would still be a planet. It might still have life in some form. But complex, multicellular, vertebrate, warm-blooded, land-dwelling life. The kind that builds cities and telescopes and fires lasers at the moon to measure how far away it is. That kind of life probably needed the moon as a co-architect. And the moon is 238,855 miles away. Right here. Close enough that we flew there with 1960s technology in about 3 days. Close enough that a laser pulse bounces back in 2.5 seconds. Close enough that every ocean on this planet rises and falls to its pull twice a day. Something the size of Mars had to die for this to happen. The early solar system had to be chaotic enough for that impact to occur, and stable enough afterward for the debris to coalesce rather than disperse. The moon had to form at just the right distance, with just enough mass to lock Earth's tilt in place, but not so much that it crushed the planet with its gravity. And here's the thing. The moon is still drifting outward, 1.5 inches per year. In a billion years, it will be far enough away that total solar eclipses will no longer be possible, because the moon will appear too small in the sky to cover the sun. In several billion years, the tidal stabilization will weaken. The axial tilt will start to wander. But that is a billion years from now. Right now, tonight, the moon is exactly where it needs to be. Step outside on a clear night and look at it. That's not an empty ball of rock. That's the thing that keeps Earth's axis pointed where it needs to go. The thing that pulled the first fish out of the water and up onto the land. The thing that was made from Earth itself, forged in the most violent moment in this planet's history, and has been sitting there ever since, doing a job we barely noticed until we had the math to see it. The most important neighbor we will ever have, hiding in plain sight, close enough to touch in cosmic terms. So here's what I want to know from you. Before this video, when you looked up at the moon, did you think of it as close or far away? Drop it in the comments. And if this changed how you see it, share it with someone who still thinks it's just a light in the sky. Hit that like button if this hit different, and make sure you're subscribed, because next time we're going somewhere that makes the moon's 238,000 miles look like a step across the room.